Hey you guys, this is going to be our last video of chapter 18 for covering the sections 6 through 8. So let's take a peek at what we have in store for us. We're going to look at corrosion. So here again, we're going to talk about this corrosion, and we are still going to work on understanding the voltages and these half cells that we talked about in the very beginning. But what we're going to look at this time is batteries. Batteries is of course, are very important in our society. Almost too important, right? If we could figure out how to get the sun to uh, charge all of our batteries, I think we'd all be good to go. But let's talk about batteries. A battery is made up of cells. Now those cells are half cells from table 18.1 are in every single one of these batteries that you're going to see. They have different, they have an oxidation reaction and a reduction reaction. So what we're going to do is look at each one of these batteries, find the oxidation reaction, find the anode oxidation and the cathode reduction reaction. So this alkaline cell here is one of the most common that you've probably seen before. This is a zinc cell. So it's a zinc cell that has a cathode and an anode. The anode is zinc undergoing oxidation. The cathode is a compound undergoing reduction. And if you check it out, you'll see that MnO2 here is going to Mn2O3. So the reduction, this guy should be what, +4. And if we look at the numbers for this one, we find out that the oxidation number of oxygen is -2. -2 times 3 is -6. So this guy would have to be what? 2x. It'd have to be 2x -6 equaling 0 to figure out your oxidation number. So that would be +3. And that is a reduction. And you can see kind of these looks like spectators, but I think they need to be there in order for this setup to work. Now, what's interesting about here is that we have a cathode. That cathode is made of graphite, and it can be made of an iron nail, but it is a lot of times it's just a piece of graphite, and that graphite is an inert surface for the reduction to occur on. The oxidation is this zinc can right here. You can see it, right? And it goes around. So over time, the zinc can starts to deteriorate. And that's why sometimes I think we see this start to leak, because over time you can get a hole in here and it'll start to leak out. So the overall reaction for this guy is showing zinc being oxidized and manganese being reduced. So that's called a dry cell. Another type of cell is a mercury battery. These are called little button batteries, and they are made of, there's a steel cathode, which is this little button right here on the top. And again, there's that zinc. So we have a zinc can that's probably going to go under, well, let's look, before we make a statement here. What is undergoing oxidation at the anode? It looks like, again, is zinc. The cathode looks like mercury. This is +2, and then this guy is 0. So there is your reduction. And your overall reaction is zinc. This is called a zinc-mercury amalgam, where they're kind of mixed together, but they're not reacting with each other, but they're both in there. Where is that? Up here. You have mercury, and you have, it's got to be in here somewhere. Either way, these little tiny button batteries undergo an electrochemical change, which then gives you electricity, but they're really tiny, and they're kind of toxic, I guess, as far as the mercury goes. This is called a lead storage battery. This is the battery that's in your car. Very heavy. It's got a lot of lead in it. And if you look at our anode reaction, you see lead solid undergoing an oxidation. If you look at our cathode reaction, you see lead, this is lead 4, undergoing reduction to lead 2. So lead is being oxidized and lead is being reduced, but in different forms. Our overall reaction then is lead solid reacting with lead 4 to make lead 2. So kind of looks like a disproportionation reaction, doesn't it? Whereas lead is going from 0 to +2, and lead is going from lead 4 to +2. So that's our lead storage battery. Next type of battery here is a lithium ion battery, or solid state lithium battery. And this is kind of a neat battery in the fact that lithium is embedded in this graphite in here. And then as the battery is discharged, lithium is oxidized, lithium plus, and runs to the other side. And as this occurs, electrons run through the device. This CO is cobalt, and that cobalt is not involved in the oxidation reaction. It's involved kind of like in a storage capacity. And I have a video that I'm going to post for you guys to look at these lithium-ion batteries and how they work. It's pretty cool. For our reactions, we have an oxidation of lithium and we have a reduction of lithium. So lithium solid going to lithium ion, it's oxidation, lithium ion going to lithium solid, and that's reduction. Let's continue on with our fuel cells. A fuel cell is an electrochemical cell, but it requires reactants. And so it's not like a battery where it's all built in, but it's redox, and that's why it's called a battery, and that's kind of why it's in this form. And I'll be releasing a video too on this one. It's kind of neat on how these work. But hydrogen in some form has to go in. Oxygen usually comes in from the air, and then the byproduct is water. At the anode, you will have oxidation of hydrogen. At the cathode, you will have reduction of oxygen. Overall, makes water, and that's why it's so nice and clean. Now let's talk about corrosion. I've been wanting to talk about corrosion for a while because I love this picture, corrosion. This is a redox reaction. This is rust. So it's okay for iron to rust, especially when these hulls are so thick. You've got iron undergoing conversion to iron 3 oxide through a couple steps. Let's look at that. So corrosion is applied to a term applied to the deterioration of metals by an electrochemical process. So as just a quick example here, this is supposed to be like a nail head, and on the surface of an iron nail, if there's water around, you will get a redox reaction in such that the iron solid is oxidized to iron 2+, and then in a subsequent step, the iron 2+ goes to iron 3. They're both oxidations with a total exchange of 3 electrons, and then oxygen is being reduced. You have oxygen element is going with an oxidation number of 0, going to oxygen with an oxidation number of -2. So this is from the air. I guess it could be in the water too a little bit. But this surface that it's occurring on is the iron nail head. So this iron surface is where you have both reactions occurring. It's like an electrode. The electrode itself is deteriorating from iron metal to this iron 2+ and iron 3+, and then oxygen is coming from the air, reacting with the iron and building up in this rust right here on the surface. So rust is a very complex process, and then this rusting, and then this rust that forms here is a hydrate. So does that mean you can scrape off rust and heat it up and then turn it into an anhydrous form? I don't know. We should try that. But either way, let's just keep moving here as far as corrosion is concerned. Here's some different forms of corrosion. This is silver corroding to make silver sulfide. That's called tarnish. And then here is copper corroding to make copper carbonate, which is called patina. Now, I've heard this word used in a couple fashions. A patina is a corrosion. I mean, there are people who do artwork with copper, and they do this on purpose. And a lot of times they'll use a chemical form of corrosion to give it a green color. I recently bought a neat piece of art from Cripple Creek, and it was used, it was old iron, and they used chemical form of corrosion to make it look greenish. It was really cool. I'll have to take a picture of it and show you. So how do we use this? I mean, corrosion can be a bad thing. So here we have an iron storage tank, and if that iron storage tank has gasoline in it or whatever, and you get a hole in it, you're going to get leakage, right, into the groundwater and into the soil surrounding. Nowadays, all of our storage tanks are completely encased in other things, but you can still use what's called cathodic protection. And that means if you want something to not corrode, like this iron, you don't want it to be the anode. You want it to be the cathode. So because if it's the anode, it's going to undergo oxidation and get destroyed. But if you couple it with something that you know will become the anode, and then this guy will be the cathode, this guy will never undergo oxidation unless, of course, this guy gets completely deteriorated over time. Then this guy, the iron, will then show up as the anode and become oxidized. So in this case, magnesium is being, since it's hooked with a wire, will be oxidized and deteriorate. This guy will not. Sorry, the iron will not. What will occur, remember this reduction reaction is what was occurring on the previous slide when we were talking about rusting. So this reduction is still occurring, but now it's occurring in conjunction with this one, not with the iron tank. The iron is being spared. This guy is being sacrificed. So as an example, if we have an iron nail, if you look at this picture, this is out of your textbook, this iron nail is attached to a metal that is preferentially being the anode. The iron is the cathode. This one was not protected, so you can see the rust going on. So basically, let's look at Table 18.1 and decide which of the following metals can act as a sacrificial anode to protect iron. So what I've done here, here's the same question. Now let's look at our table and let's find iron. Here's iron. And let's find all these other metals. We have lead, we have cobalt, we have nickel, and then we have strontium. So the question is, which of them can act as a sacrificial anode? So which one of these substances or metals would be more likely to be oxidized? And I'm going for strontium. Strontium is more active. It's more likely to be oxidized, and look where it is in its EMF compared to the iron metal. So these would not act as a sacrificial anode. If you couple these substances with iron, iron would be the anode, and it would be deteriorated. Now let's keep on going with electrolysis here. We're still on electrochemistry, but now instead of spontaneous reactions, we're going to look at non-spontaneous reactions that can be caused by plugging it in, if you will. Electrolysis is the process in which electrical energy is used to cause a non-spontaneous chemical reaction to occur. For example, the electrolysis of molten sodium chloride. And I have a video that I'm going to put out on this one too. I didn't want to insert the videos in these. It would make this too long. So as far as when you electrolyze something, molten means to be melted. So you melt it, you put in your electrodes, hook it up to a battery source like this, and you force an issue. You force electrons to run to the cathode, you force electrons to be removed from the anode, and at the anode is oxidation, at the cathode is reduction. So this is definitely creating substances that are higher in energy. So I'm putting energy in and I make chlorine gas and sodium liquid, very reactive stuff. So obviously you could not run this in a beaker. It would melt your beaker, but this you could. This is called a Downs cell, and a Downs cell is a method of creating or splitting salts. You can split sodium bromide, lead bromide, sodium chloride. It doesn't make any difference. Now, electrolysis of water is slightly different, but it's kind of the same in the fact that you are splitting the water molecule. You're going to cause an oxidation to occur at the anode, a reduction to occur at the cathode. In this situation, hydrogen is being reduced and oxygen is being oxidized. So we have -2 to 0 for this guy and +1 to 0 for this guy. So again, that's being a higher energy situation. Hydrogen and oxygen are higher energy than the water molecule. And there's what you would see. You would see bubbles occurring at both of the electrodes because hydrogen is produced at one, oxygen is produced at another, but you will see it's you're getting twice the amount of hydrogen than you are of oxygen because of the ratio. Remember, if you write the chemical reaction for the electrolysis of water, you will see water being split to hydrogen and oxygen. And where do we see that 2-to-1 ratio? If we put a 2 here, we have to have a 2 here. So 2-to-1. For every two molecules of hydrogen, you get 1 molecule of oxygen. And you would see that experimentally up here in your experimental setup. All right, let's just do a quick review of concepts to see, and I have a video included here. We'll see what we can do. So as far as this is a kind of very similar to the down cell that we saw before, but now it's magnesium chloride. The question is, complete the electrolytic cell by labeling the electrodes. Well, if if one of the electrodes is hooked up to the negative of terminal of the battery, that is where the electrons are going to go being pushed towards. Then this one is where they're taken from. So if electrons are taken from here, it's feeling positive, and electrons will go to it. And on this, chlorides will be attracted to it, chlorides, and those chlorides will gain those electrons, lose those electrons and become chlorine. Now on this side, electrons are feeding down into here, and those electrons you would have Mg2 plus being attracted to that electrode, and when they would be attracted to that electrode, they would then gain those electrons and be reduced. And you see I have a mistake here. When I cut and pasted earlier, this should not be that. This should be Mg2 plus 2 electrons. That's what you get for cutting and pasting to make magnesium solid at that electrode. So this guy is incorrect. Sorry about that. Let's see if this video works just for fun here. Actually, it doesn't look like it's going to work. It looked like it went on and then stopped. So I'll go ahead and, this is electrolysis of a melt. And it's kind of cool because you melt it it's like an evaporating dish over a Bunsen burner. And then you put these look like graphite. See right here, I can't write on here. Both of these are graphite electrodes. And then you hook them up to a battery, and sure enough, you get bromine. This is lead bromide, if I remember correctly, PBr2. And then you get lead metal at one electrode, and you get bromine, liquid bromine, and red bromine vapor at the other electrode. Hey you guys, now we're on to the quantitative aspect of electrochemistry, which means quantitative means how much, right? So we can run, or of course when electrolysis is set up, it's connected to a battery. The battery is going to deliver electricity in the form of electron flow, and that's measured in amps. So if we can measure that and we know how long we ran it, what we can do is determine how much charge has run through the system. And the charge, if you remember from half reactions, the charge is related to the number of electrons that run, and the number of electrons that run is related to our half reactions. So for example, from the previous slide, we were making magnesium metal. See, I almost messed it up again. Plus 2 electrons. So if I know how long I have run my cell, if you will, that Downs cell, then I know how many electrons I have delivered. And I can determine that by how much current I applied for a certain amount of time. And that gives me charge in coulombs. Now you remember coulombs is related to moles of electrons through the Faraday constant. So we see that here for every 1 mole of electrons relates to 96,500 coulombs. So if I run so much current for so much time, and that turns out to be 96,500 coulombs, I have just delivered 1 mole of electrons. Now, if you look at my example here, that means I would have created a half a mole of magnesium. So I would have to do this for twice as long to get 2 moles of electrons, to get 1 mole of magnesium metal at that electrode. So that tells you how much charge is transferred per mole, and it's used in the next problem. So let's continue to look here. Your book gives this really good little flow chart that guides you on how to do something like this. If you run a cell for so much time with a certain amount of current, if you multiply those, that tells you the charge. Then you can divide by the Faraday constant, because the Faraday constant is this 96,500 coulombs per 1 mole of electrons. So it's like a conversion factor to convert between charge and number of electrons. Then I can use the mole ratio like I was talking about up here. For every 1 mole of magnesium, 2 moles of electrons need to be transferred. I can use that to determine how many moles of magnesium should show up at that electrode, actual metallic magnesium. Now, if it's in grams, I could then use the molar mass to get convert from moles of magnesium that I got up here to mass, or if a gas is produced, I can use the ideal gas equation to determine the number of liters. So this flow scheme can run in either direction. If you know how long you ran the cell, we can calculate how much in grams of solid or liters was produced. And that goes in the reverse direction as well. If I know how many grams were produced, I can figure out how long I ran the cell or how much current must have passed. So let's look at this example. How much calcium can be produced in an electrolytic cell of molten calcium chloride if a current of 0.5452 amps is passed through the cell for 1.5 hours? So now, what could be the anode here? It's calcium chloride. So this is going to be the reverse of what we would think it was because this is electrolysis. So normally, running downhill, calcium likes to go this way, but now it's an electrolysis. So he is at the cathode. Calcium is being reduced to calcium metal. And at the anode, chloride is being oxidized to chlorine gas. The overall reaction for this electrolysis is calcium. Now this is wrong. This should be aqueous, don't you think? Oh, no, it shouldn't. No, it shouldn't. It's liquid. My bad. Because it's molten. So for those 2 electrons, for every 2 electrons that run, 1 mole of calcium will be produced. So let's use our electrochemical data here, or our charge data. The 0.452 coulombs is a value that was given up here, which is amps. And remember, amps is a coulomb second, because remember, coulomb was equal to amps times seconds. So that means an amp is equal to a coulomb second, and that's why it's like that. Sorry about my drawing. Okay, so now what are we going to do with this? We know we ran it for so many hours, but of course it needs to be in seconds. And then we use Faraday's constant to get how many moles of electrons that is, and then use your mole ratio for calcium. And if you cancel out all your normal, all your units, you're left with moles of calcium, which is what was being asked. And then if we want to take that to grams, we could by using molar mass of calcium, just like our normal thing, moles of calcium and grams of calcium. Okay, so that ends this PowerPoint presentation for the last half of Chapter 18. Dive into the fun sheet now and see what you can do with this.